Hello everyone, welcome back. First of all, a very happy new year to all of you. This is the sixth lecture of the series Electrical for GATE and IES in 10 minutes. In this lecture, we are going to study about Laplace transform in more detail. So this is all about me. You can read it from here. So in this lecture, we are going to study about Laplace transform, its properties and related numericals. First, let us discuss the evolution of Laplace transform or the relationship between Fourier transform and Laplace transform. As you all know, Fourier transform, it gives the behavior of a signal in frequency domain. Basically, it expresses a signal as a continuous sum of complex exponentials. This is given by the formula f of jw, the Fourier transform of f of t, a time varying signal f of t, that is given by f of jw is equal to integral from minus infinity to infinity f of t e raised to power minus j omega t dt. The problem with Fourier transform is that it is not possible for a large number of functions for which Fourier integral is not finite. Basically this integral which is not finite. One very good example is a ramp signal. Now this problem is overcome in most of the functions by introducing a convergence factor, which is basically a negative real exponential. It makes the Fourier transform possible, and the resultant transform is known as Laplace transform. So it is given by Laplace transform of f of t is equal to Fourier transform of e raised to power minus at f of t. So this will be integral from minus infinity to infinity f of t e raised to power minus st dt. S will be equal to sigma plus j omega. Now since we are concerned with causal functions most of the times, and for causal function is there for t is greater than or equal to 0, so Laplace transform of f of t will be equal to 0 to infinity f of t e raised to power minus st dt. So in this way we arrive at Laplace transform of function f of t. Now let us study about some important properties of the Laplace transform. First property is linearity. Basically it states that Laplace transform of a combination of two functions a f of 1t plus b f of 2t is that will be equal to a f1s plus b f2s. So basically that will be equal to individual Laplace summation of individual Laplace transforms. Second property is frequency shift or scaling. So Laplace transform of f of at is equal to 1 by a capital F s by a. Very easily derive these properties by using the definition of the Laplace transform. That you do it yourself. If there is some problem, please please post your problem in the comment section and I will clarify it. Next is differentiation with respect to time, that is equal to s f of s minus f of 0 minus you have to remember all these properties. It will be very useful to solve the numericals that you will see later. So you have to mug up these properties. Next is integration with respect to time, that will be equal to f of s by s, then multiplication by t, that will be equal to minus d f of s by ds, then right shift in time, then convolution in time, then division by time. So you have to remember all these properties. Now let us see Laplace transform of some typical functions. Basically we will be using the properties discussed in the previous slides to derive Laplace transform of these functions. So these are important. You have to derive them by using those properties. So first is a unit step function. Unit step function is the definition is ut is equal to 1 for all t greater than or equal to 0 and is equal to 0 for t is less than 0. So we will just write the definition of Laplace transform, the basic definition, and we get the Laplace transform of ut as 1 by s. Now Laplace transform of an exponential function e raised to power at ut. So we know Laplace transform of e raised to power at f of t is equal to f of s minus a by using the property discussed earlier. So Laplace transform of e raised to power at, that will be equal to 1 by s minus a, because Laplace transform is of ut is 1 by s. Then Laplace transform of sine of omega t. Now sine of omega t is equal to e raised to power j omega t minus e raised to power minus j omega t by 2j. So the Laplace transform will be individual Laplace transforms of these. So that will be equal to 1 by s minus j omega minus 1 by s plus j omega. On solving, we will get omega by s square plus omega square. You have to remember these also. It will be useful to solve the complex numericals very easily. Similarly, you can find out the Laplace transform of cos of omega t, that will be equal to s divided by s square plus omega square. Then do it to two more functions, sin h hyperbolic sin omega t and cos h omega t. You do it yourself and paste it on the comment section. Now Laplace transform of function f of t is equal to t. That comes out to be 1 by s square. So you can see that if we try to solve it through the definition, it is very difficult. So we will be using a trick here. So Laplace transform of t, that will be equal to Laplace transform of t into ut. So any function multiplied by t, its Laplace will be differentiation of the function. So it will be equal to minus d by ds of Laplace transform of ut. And ut is 1 by s. So differentiation will be 1 by s square. Laplace transform of t is equal to 1 by s square. By corollary, you can derive it. Laplace transform of t raised to power n f of t is equal to minus 1 raised to power n dn f of s divided by dsn. So remember these the Laplace transform of these functions. It will be very useful. Now the Laplace transform of delta t. So delta t, an impulse function, is equal to 1 for t is equal to 0 and it is equal to 0 for all other t. So delta t, this is equal to differentiation of ut with respect to time. So its Laplace will be equal to differentiation of ut. So that is equal to s into 1 by s by using the property 3. You can see the property 3 here. So the Laplace transform of delta t is 1. You remember this. Now let us see some numericals. We will use the properties as well as the derivation of important functions which we discussed in the earlier slides to solve these numericals. First is t square sine of omega t. So we know that Laplace transform of t raised to power n f of t is equal to minus 1 raised to power n dn fs divided by dsn. So Laplace transform of sine omega t is equal to omega s square plus omega square. This sine omega t is capital F of s in this numerical. So we can just substitute and solve it. On solving, we will get it equal to minus 2 omega s square plus 8 omega s square divided by s square plus omega square whole cube. So it is simple. You try to solve it. If there is some problem, post it on the comment section. This sine omega t by t. So here we will be using the property that f of t by t Laplace transform is equal to integral of f of s ds from s to infinity. And sine omega t, we know its Laplace is omega divided by s square plus omega square. So on substituting and solving, we get it equal to pi by 2 minus tan square s by omega. Next is 1 minus e raised to power minus 2t ut. So it is also very simple. Simply separate these and solve for the Laplace. So it will be equal to 1 by s minus 1 by s plus 2, that is equal to 2 divided by s into s plus 2. So next is sine of omega t minus t0. Sine of omega t minus t0. So first you solve sine of omega into t minus t0. You just expand it. It will be equal to sine omega t minus sine omega t cos omega t0 minus cos omega t sine omega t0. Note here that cos omega t0 and sine omega t0 are constants, so they will be out of the Laplace. And on substituting the Laplace transform for sine omega t and cos omega t, we will get this. So that's all for today. Thank you for watching the video. If you have any doubts, please contact me. You can contact me on the comment section in this YouTube, or you can send an email, and there is a Facebook page also. So do rate and review, like, comment and share and subscribe. Please share it with the relevant audience so that more people can be benefited from it. Thank you.